When's the lab verification grade supposed to be up? I'll talk about this too when lecture starts. I want to get it done as soon as possible, hopefully tomorrow. But there's a lot of work to do. There's just a lot of data that we got to process. But I do like to get the lab stuff done as soon as possible. Hopefully tomorrow. We had some scheduling miscommunications this time around, so we do have a decent number of the students in the class interviewing today. So I can't get it done any sooner than tomorrow, but I'm hoping to get it done as soon as possible and get it done tomorrow. Yeah, best. That's what I'm talking about, but the best part of the day. Unless you hang out for 442 as well. I'll accept that, but... Yeah, face detection, that is the... Face detection and physics engine, that's the part that takes that from like a 115 assignment up to a 116 level assignment. Without face detection, that homework would be honestly pretty easy. Yeah, and we got to learn some state pattern. All this week is state pattern to be able to do calculator and microwave. Can I ask about test cases for the homework after lecture? You can ask anything you want. After lecture, I'll probably have time to address it. Now, we hit 150, so I do got to start lecture proper. What to explain in the interview? Yeah, all right. So let's get started. The first thing I want to talk about is this homework deadline that was last night that we had, the whole class in a panic, of course, as every deadline. What I want to talk about with this are the extensions. I posted on Piazza, but for those of you who haven't checked Piazza yet or whatever, or if you're watching this on YouTube, just double check the AutoLab feedback. Go to your AutoLab, and there's some data in this homework program execution. And just to clarify, because we had this question far too many times yesterday, you submitted your homework, the auto-graded portion of your homework, to these application in the objective itself, and then you also have an interview for that homework. The interview and the code combined determine if you've completed that application objective. And then for the application objective, we're going to use this assignment in AutoLab just to share your grades with you. Same for all these learning objectives. You'll never make any submissions to any of these. These are just for us to communicate to you that you've completed one of the learning or application objectives. So if you go to your homework program execution, I don't have any grades, so can't show you the full thing. But go into your grades for homework program execution. There will be 3 problems in here: code, interview, and verification. And by the way, there's been confusion about this as well. I want to clear up. The numbers really don't mean anything in AutoLab. They're strictly informational. They're not like a grade in other courses. So those of you who got the primary objective in AutoLab is saying 0.5, don't sweat the number too much. I just want that number to indicate that there's still more for AutoLab to assess you on in that objective. Some of you got a 0.5, and I gave you credit for the code, a 1.0 here. So here, this is going to be 0 or 1. And you either have a 0, 1, or actually a 0.1, but again, it's just informational. For code, check your score for that, and then click on your score for the code portion, and that'll tell you your information about whether or not you have an extension or what and why. I'll give some brief description. You have an extension. Here's your new deadline. You don't have an extension, etc. And then some information about why I made that decision. So take a look at that. If you don't have an extension and you didn't complete the code, you can no longer complete this application objective. If that describes you, you are no longer playing for an A. You missed this opportunity for this application objective. You're aiming for an A- at best at this point. That was a big deadline that passed. If you didn't even attempt the homework or made some just superficial submission or some last-ditch effort attempt after skipping the lab, for example, then you can't complete that objective anymore. You missed your chance. You took several weeks and you did nothing with it, or little to nothing. You can't do that anymore. If you have an extension or you completed the code, look forward to the interview this week. Your TA should have already contacted you and gave you information on how to schedule that interview. If you've completed the code, once you complete the interview, I'll go in and verify and check this last one. Once you get the verification 1.0, that's me reviewing everything and just making sure everything's on the up and up. Once I mark off the verification, then you have completed that program execution application objective, but not until you get the verification point. If you have code in interview, it's only going to be rare cases where I'm not going to verify, but I do want to put my stamp on it to make sure that everything's legit. Similar with the learning objectives, we're going to be populating the program execution learning objective. This goes right by the syllabus. The syllabus goes through what this read, write, explain, and verification are. Once you get the verification point, you have completed that learning objective. So we'll be grading, hopefully, again, like I said, Tuesday, tomorrow, we'll be able to get that done and get the first round of feedback. And then your feedback is going to give you what you need to do. So you'll be able to click your scores, get your feedback. Okay, read, I didn't get the point, let me click on it. Okay, it says I did very poorly on the Thursday lab, and here's how I can make it up. For the reading portions, you'll be able to make those up in future lab quizzes. And also the very last week of lab is just strictly makeup, so you'll be able to make up any of these on the last week lab, that last Thursday of the semester. But also I have some built in where you can make these up in future labs. So for example, going through the stack and heap memory that you did on this one, I'll have questions on later labs that ask you about stack and heap memory, and I can use those to verify your reading ability for this bullet point, which was following the stack and heap. I'll get the exact wording here. Read, trace through a program, and trace the state of the stack and heap memory through its execution. So I'll have questions that are exactly like that in later labs. For example, in functional programming, we're going to look at recursive method calls, and I'm going to ask you to trace through all of the stacks, the frames on the stack throughout that execution. So that's one way that you can make that up. And also immutable objects and how they work in the heap space. Those are both parts of functional programming. So I'll have naturally built into that quiz ways to make up this bullet point. So just an example of the future opportunities that you'll have for that. For learning objectives, I'm going to keep giving you opportunities. Like I just said, a lot of it's built into the course already, but I'll keep giving you opportunities since it is, 5 or fail. You have to complete them all. You have to complete all 15 bullet points, 3 for each of the 5 learning objectives, in order to pass the class. So I'm going to give you more opportunities. I never want the possibility of you having just one bad day. Maybe you didn't get enough sleep for an interview or something. I don't want that determining whether you pass or fail the class. So that's why it's all built like that. And I haven't expanded on this as much as I have have last semester, so I want to say this one again. Your goal in this course is to convince me that you've completed all 5 learning objectives and all 15 of their bullet points. You can do that in many different ways. So if you miss one of the opportunities, you're going to have more opportunities to be able to prove that to me. But as long as you convince me, if you put forth a convincing argument that you've completed the bullet points, I'm gonna give you a passing grade in the class. That's not quite the same with application objectives. That's where you're really earning your way up to an A or a better grade or the grade that you want. So those I'm going to be a little more harsh because we just saw the first deadline pass. If you haven't been trying, you really should just be focusing on the learning objectives at that point. Make sure you understand what's going on with the course. But the learning objectives, I'm going to keep giving you opportunities. So your goal is to convince me, a human being. I'm going to be reviewing this along with the TAs, and I'll be verifying it. As long as you can convince me that you can actually do these 3 bullet points, well, for program execution, these 3 bullet points, I'm going to give you completion for program execution. But it's up to you to provide me with that evidence by submitting to Autolab, submitting quality labs, doing well in the interviews. You have to give me the evidence, so when I look at all the evidence that you provide for me, I can look at the case that you're bringing to me, and I can say, okay, you've definitely completed these. Here's credit. If you slack in one of those areas, there's going to be a bullet point that you're not getting. You're not going to get that verification. You're going to have to do either a makeup interview or makeup lab, or actually complete your lecture questions. And the goal, I've said this before too, worth repeating, the goal is for you to focus on being able to do these things. These are all written as things that you will be able to do by the time you're done with this class. I want you to be able to do these things. I don't care about what percentage you got on some quiz or whatever. I don't care about some arbitrary points. I care if you can do these things. Show me that you can do these things, and you'll pass this class. So focus on the education, not the grading structure. I mean, understand the grading structure, of course, but don't be like, oh, I got to get 100 instead of a 90 on this thing, because mathematically that's what I need to do to get a B+. Or we don't want any of that in this class. Expansion objectives can be completed until the after the last day of class, December 13th. So when you interview for physics engine, if you didn't do the expansion objective, you can still interview for that later at some other point in time. But you have to have them all done by December 13th. Yeah, interviews are stressful. You should be stressed for interviews. And part of the point of the interviews is to prepare you for that eventual internship or job interview. It's going to be a very similar structure. You're going to have somebody grilling you on technical material. You're going to go through that, presumably 10 times in this course. Possibly fewer if you didn't do some of the homeworks, possibly more if you have some makeups. But you're going to get a ton of practice for that interview for an actual job. So that's part of how this course is built. It's preparing you for that. Because usually you don't get any. I don't think I got any experience with that before my first internship interview. All right, but let's get into any more quick questions. Actually, I want to pause for a second. Just to make sure I got all the questions out of there. Because I know the grading in this course is very different than anything else you've seen before in other classes. So I just want to make sure we're on the same page. I know I've been talking about it a lot, and I'll continue to talk about it until we're all on the same page on how this course is graded. What it comes down to is the objectives, and they're graded by a human being looking at the work you've produced. So some of you didn't get all the AutoLab stuff done for the homework, but still got completion for the code because you had enough there. Some of you might get completion for the code marked off during the interview. If your demo goes great and you're like, I don't know why AutoLab doesn't like me. Look, it works perfectly. In those cases, I plan on giving you credit for the code, even if AutoLab isn't happy. I don't want one line in my autograder or one of my autograder test cases denying you an application objective. Would TAs answer homework-based questions in office hours? I mean, it depends what you're talking about. They're not going to give away the solution, obviously, because there's still people working on the assignment. But they'll always help you. They'll always guide you a little bit, especially if you're confused as to what the assignment is even asking. They'll always help you with that. And you can go with your code. You might not always be satisfied with their answers. I know that's a common complaint because they're not just going to give you the answer. They're not just going to tell you what to write or what you need to do, but they will guide you. They'll help guide you. They'll say, well, think about what happens if you do this, or run the debugger and show me what happens when it executes. They'll guide you like that. They shouldn't be giving you any answers anyway. So we don't have grades in program execution yet. It depends which one you mean. You don't have any grades in learning objective program execution, but you do have the code grade for the program execution application objectives and the feedback of whether or not you have an extension. Can I still do the other application? Yeah, if you did one of the assignments and you still want to do the other one as an expansion objective, that is, again, due December 13th. So there will be a mess of interviews at the end of the semester. I'll probably be doing a lot of interviews during that time while you're doing all your expansion objectives. It's going to be a mess. I should have set it up different, but I don't really have a good answer for that. I got a 1 in the code, but one test case that doesn't. Can I address that? I mean, yeah, we can still talk about it. You don't need that last test case for your grade. So when I looked at your code, when I looked at your submission, I overlooked that and said, you got the primary objective. You're good. You're good to go on the code. So you don't have to, but if you are curious, we'll be happy to talk about it in office hours. Okay, so let's talk about states. Let's get into the good stuff. Enough with the course logistics. Presentation. I know y'all want to talk about grading all day, but we can talk about that again at 2:40. All right, the state pattern. So this week, and by the way, most of the class, if you're behind right now, most of the class is in the same boat. The class is usually behind at this point, but it's definitely worse this semester. I think it's because we started out online only, and I think a lot of students are just having trouble focusing and managing their time when they're in a different environment. Usually, if you're on campus, you're used to working. You understand that you're there to work. But if you're at home, things are just a bit tougher. So things are quite a bit worse this time around. The nice thing is I do have some parts of the course built in and structured in order to help you catch up, and this week is one of them. Because, I mean, it might not feel like that to you, but this week is going to be just one topic, the state pattern, and I'm going to talk about technically everything you need to know about the state pattern today, and then 2 days of examples and reinforcement. So we do have some time to take somewhat of a breather, though if you're having trouble understanding the state pattern, of course you might need the whole week to get this down. But we're going one topic in an entire week, where at the beginning of the semester we were covering sometimes multiple topics in a single lecture. So the pace of the content is slowing down, though the complexity of the content is going to start ramping up. And we'll see that more throughout the semester. So, state pattern. Let's do it. So the big thing with the state pattern, I'm forcing you to use the state pattern by denying your control flow. So just like the calculator and microwave homeworks, all the 3 lecture questions this week are going to ban control flow. If you use any conditionals, any loops in your code, you're going to get a compiler error and a 0 in AutoGrader. I do that by removing all of your control flow and replacing it with redacted and a bunch of stars, if you ever see that in AutoGrader. And I do this through all of your code, and then any Scala files that you submit, I compile all of them. The implication of this is if you have one big project with all of your code, and you've been submitting that for every lecture question, for these 3 lecture questions coming up, you're going to have to put those lecture questions in a separate project or put them in separate zip files when you're done with the code and submit just that lecture question or just the lecture questions with no conditionals. Because if you have one conditional from another lecture question, it's still going to be an error in AutoGrader. So don't fall into that trap. If you see that stars with redacted and your code doesn't compile and you get errors in Autolab, it's because you had some control flow somewhere in your submission, even if it wasn't related to this lecture question. So just be cautious of that. Heed my warnings on the bottom here, and make sure you're not falling into that using control flow. No control flow for these things. For these questions, these state questions. And that's strictly my way of forcing you to use the state pattern. Although with this one, you can technically get away without using the state pattern. I don't recommend it, though, because you got to learn the state pattern to get the next 2 lecture questions in the homework. So, without further ado, you want to create a player class or the constructor that takes no parameters that can move through 3 different states, running, ducking, and standing still. And it has these methods in its API. Duck, which enters the duck state as long as the player is standing. You can't go from running to ducking. A stand still method, that whether the player is ducking, running, or standing still, they're going to be standing after that method is called. Run, which enters the run state, but you can't go from ducking to running. So if the player is standing and run is called, then they are now running. And then 2 methods, jump height and movement speed, which returns how high the player can jump and how fast the player can move. These methods are going to return different values depending on the state of the player, whether the player is ducking, standing, or running. If they're ducking, we're going with the Mario 2 idea that you can do a super jump when you're ducking. Standing a little less, and then running you can jump really high. Movement speed, very slow, ducking. Fine standing, you can walk, and then running faster. So what we would naturally want to do is have a variable that tracks the state of the player, and then in jump height and movement speed say if player is ducking, return 4, if player is standing, if player is running, etc. But we can't use control flow, so how the hell do we do this question? And also a test suite, test player, and you can also have no control flow in your test suite also. You have to test without any control flow. So be cautious of that as well. Which isn't too big of a deal in my test cases for this particular question. I was never tempted to use control flow there, so hopefully that's not an issue for anybody. And as always, only call the API methods. Only call anything that's defined in this question itself. If you call anything else in your test suite, when that test is ran against my code might not have that same thing, that same method, that same variable. So you can only call the API methods defined here. So you would call duck, stand still, run in some combination, and then call jump height and movement speed, and make sure you get the right value through an assert. Say assert jump height equals 4 because I expect the state to be ducking, etc. So, yeah, ellipsa. That would be a pretty easy lecture question. I mean, that would be like a first half of 115 lecture question if you could use control flow. It would just be a question about control flow. Without control flow, oh boy, let's talk about the state pattern so you can wrap your head around how to do something like that. So design patterns in general, we're talking about just the state pattern specifically, but design patterns in general are approaches to common problems in programming, and specifically object-oriented approaches. So using OOP, how can we use objects, inheritance, and polymorphism to solve common problems that come up in our programs? So there's solutions to these common problems. If you're interested in other design patterns, which I hope you are, your search term is the Gang of Four. Check them out. It's they're kind of the people who came up with the initial set of design patterns. There's a variety of design patterns for common situations that you can help that can help you organize your code in interesting ways. And as always, this is as we're talking about OOP, and as we'll talk about in FP as well. Most of our goal here is to simplify our programs so we can add features easily, we can test easily, and we can maintain our code much easier. It should be easy to onboard new developers, have them understand what our code base is doing, reuse our code, maintain our code. A lot of things that apply pretty much only when we have larger programs. When you have the 115 size programs, the stuff, if you had to rewrite your whole program, who cares? But as we're writing larger pieces of code, it's a lot more important to design for maintainability. How do I add a feature that a customer is requesting? What if we want a new feature? Like we saw with OOP last week. What if we want to add more objects to this game, more inanimate objects? We want to make that easy to do and easy to expand our code. So even a large code base, it's easier to make it larger and add new features to it. Didn't know this was a history class. I barely gave any history. Do It Small gave more history than I did, I guess. So the state pattern, we can't use the state pattern without good old polymorphism. So good thing we understand what that is now. Where we're having objects of different of one type stored in a variable of a different type, of a type of one of its superclasses that it extends. So we're going to leverage that fact to enable us to use the state pattern. So just a reminder, every object in Scala is going to have state and behavior through variables and methods, and we're usually using the state to change the behavior. So in our behavior, in our methods, we can ask those state variables what their values are to be able to have some different behavior. So maybe we have a conditional that says if this state variable is some value, have this behavior, else have some other behavior. Or maybe we just have a mathematical function where we want to say, give me the distance from this vector to this other vector. And you just run some numbers according to the state variables of that vector and the state variables of the input vector, compute the distance, then return that distance. But we have different behavior the behavior depends on the state. the values in those variables. But what if we want to significantly change the state or the behavior of an object based on its current state? This is what we want to do with the state pattern. So our natural thing to do would be this. This is probably the first thing you would think of when I said that. Probably the first way you would approach this and code this, you would have a conditional. If some condition, some behavior, else some completely different behavior. Perfectly fine code. And again, I want to reiterate this because I've had this misconception before. I'm not saying there's anything wrong with this. This is perfectly valid, cool, good code. This is something we do very often in programming. I'm just showing you an alternative through the state pattern. I'm not necessarily saying the state pattern or the conditionals are better or worse. It all depends on the specific situation that arises. So this will work, but how do we maintain this? The issue with this, where this becomes less attractive, is when you have multiple behaviors, when you have more than two. In this example, if some condition, some behavior, else, if, else if, else if, else if, else. And we have like 5 really different things that a particular object wants to do. One method in this object, I want it to do very different things based on a bunch of conditions that can occur and have very different behavior. This still works. It's okay. It's definitely getting worse now than when it was just one conditional and an else. But this gets much harder to read when each of these behaviors could be very complex. This could be a method with several hundred lines of code. So it's hard to read when you're trying to onboard new developers. It's hard for them to get a grasp of what is going on with this thing. It's hard to maintain. If you want to add another behavior, for example, you have to retest everything in this method. So what if I add another else if right here? I've already tested all these conditions. I made sure I gave it conditions that hit each of these behaviors and then check if each behavior is behaving the way that I want it to. And I have this huge test suite with maybe 500 lines to test every possible branch of this conditional. And then I add an else if right here and have other condition 0, other behavior 0. Well, now I might have just invalidated a large portion of that test suite. I have to go through and retest this entire method, including all of this behavior and all of these conditions, to make sure that that new condition didn't interfere. Maybe that new condition is true in some case where I wanted other condition 2 to be true and other behavior 2 to be had. So I have to go through all my tests and redo everything. It's just a mess when you want to add new features. This is the kind of code where you write it once, it's basically held together by duct tape. You hope it works, and if it works once, you don't touch it again because it's so brittle. It's so this code's so vulnerable to bugs that once it works once, you just don't touch it again. That's not how we want to code. We want to be able to add new features to our programs when our customers ask for it or when we want to add them. So we want a better approach here. So this is where we're going to use the state pattern. So let's start talking about the state pattern. Enough introduction. Let's talk about what this thing actually is. So instead of changing the behavior of an object based on a value, based on the value in its state variables, we're going to make decisions based on type using polymorphism. So we're going to have a variable that's going to contain the current state of an object, which controls its behavior. We're going to defer to that state object for our behavior. And through polymorphism, based on what type that variable actually stores at that given moment, is going to determine what behavior we have at that given moment. So now each of those behaviors will go in a different class that extends the state type, and then we'll set that variable containing the state of that state type to whatever, an instance of whatever class we want the behavior to be for this object at a given time. I feel like I use like 6 different OOP terms in that single sentence. Don't worry, there will be examples. So now we have a lot more classes, a lot more object types floating around, but they're all smaller, so they're easier to test without breaking any existing features. So we declare our state class as an abstract class. We define its API, which is a term I'll start using a bit. This stands for Application Programming Interface. I'll use it to mean, and it has a lot of different applications, this acronym. I'll use it to mean the list of methods that can be called. So the state class, an abstract class, is going to define which methods can be called, but it won't define their behavior of those methods. It's just going to guarantee that anything that extends it is going to have those methods defined. Then we extend that state abstract class for each state that the object can be in, which captures each of these unique different behaviors, which can be very different. And each of those classes is going to define one actual state that this object can be in, and it's going to define those methods based on the behavior that's expected from that state. And then each state is going to have a reference to the object to which it's attached, which means it can access all the state variables of the object that contains that state. And also, each state can replace itself and change the state of the object that it's attached to. And that's going to be extremely important, and we'll see why. Was a state pattern used to create the template of the physics engine? Yeah, and Wednesday is going to be going over that example. So the jumper game uses the state pattern to get some pretty complex, fairly complex jumping behavior. If you notice when you play the game, if you just jump, you jump at one height, but if you're moving and jump, running and jump, kind of like today's lecture question, you can jump higher in that game based on moving or not. You can also double jump, and you can jump after you walk off a ledge too. You can kind of use that double jump even if you don't initiate a jump. And we'll talk about that in depth on Wednesday. We'll go through that example. There's a reason I put that example in that homework. So if you did rhyming dictionary and haven't looked at the physics engine homework, at least get an idea of the code that's provided, because there are great examples of polymorphism throughout that code base. And we'll talk about it, the jumping behavior, properly on Wednesday. All right, so I just said a bunch of jargon, basically. It's okay if a lot of that went over your head, as long as some of it stuck and you have a somewhat kind of idea of what the state pattern is. So we're going to go through an example to explain what this actually means. What did I just say? What was all that? Just defining the state pattern. So let's use an example. We're going to look at the cool-headed Bruce Banner. He's a world-class scientist. He can successfully drive a car, but he's not very helpful in a fight. We're going to refer to him as Dr. Banner here. And let's meet somebody else. If you're not familiar with the Incredible Hulk, if you make Bruce Banner angry, he tends to change into the Incredible Hulk. The Hulk has very different behaviors than Dr. Banner. The Hulk smashes cars. He's great in a fight, and he's a bit out of control. So we have one man and two very different sets of behavior that we want to change depending on which state he's currently in. Is he currently Dr. Banner or is he currently the Hulk? Because he's going to behave very differently in each one of these states. So let's simulate this in code. Let's grasp what this looks like in code. And of course, we're going to use the state pattern here. So we're going to create one Bruce Banner class with the behavior of both of these states. And instead of having that class define the behavior in each state, we're going to defer to different state objects to determine how he's going to behave. So when Bruce Banner and Dr. Banner and the Hulk behave very differently in terms of using cars and fighting, the two API methods I chose here, we're going to have that behavior change depending on the type stored in the state variable of Bruce Banner. So let's look at some code. You don't want to see me angry. So let's look at the Bruce Banner class. And we're going to notice that there's not a lot of code here. There's almost no behavior or much state, many state variables. We just have a variable named state of type state. And we're going to initialize this to some Dr. Banner class that we haven't seen yet and pass a reference to Bruce Banner to the Dr. Banner object that we're creating. And we'll see that when we get to the Dr. Banner class. And then all of our methods, we have 4 API methods. The methods that can be called on Bruce Banner: make, angry, calm down, use car, or fight. These 4 methods in the Bruce Banner class don't have any functionality implemented. they just defer to the state for their functionality. So if I call make angry, if I have an object of type Bruce Banner, I have a reference to Bruce Banner, which could be an object where we only expect one Bruce Banner to exist. We have a reference to a Bruce Banner, and we call make angry. Make angry is just going to defer to the state. Now, whatever type the state is, it's of type state, the variable, but what actual type, in this case Dr. Banner, is stored in the state, we're going to get the functionality from that type that's overridden from the state. That's how we're going to change the behavior of Bruce Banner based on his current state. So let's look at all the code. Let's get bigger here. Since I made my face hole big enough for this one. So let's look at all the code here. So the state abstract class here is just defining the methods that can be called by any state. And I'm leaving these all as abstract methods. We could have some default behavior inherited by every state if we want. And I do that in the jumper game a few times. But here I'm going to make all these methods abstract. I'm just going to say any state that Bruce Banner is in has to implement these methods. Make angry, calm down, use car, and fight. Dennis Grace, you didn't have to at me on that one. Oh, you didn't at me. It just highlighted it anyway. Yeah, I don't even get mad at AI violations anymore. I have a very calm, accepting, here's your F these days. I stopped getting angry over those. It's still upsetting, but I mean, you're mostly hurting yourself. And I'll be happy to hand out the F. Not really happy, but you know, it is what it is. Anyway, the state is going to define what methods can be called, and its constructor is going to take a reference to the object to which the state is attached. In this case, the object of type Bruce Banner. Now, when I create the actual states that Bruce Banner can be in, Dr. Banner and the Hulk, I'm going to extend state. I'm going to have a constructor that takes in a Banner object and forwards it to the state. I have the same variable name because this is all inline in the constructor. I can get away with that. If I had to use this dot banner equals whatever, I wouldn't be able to get away with that. But here, it's all inline. I'm going to do that. And now, since I extend state, I have an obligation to implement all four of these methods. So now when I write the Dr. Banner class, I'm going to implement these four methods in terms of what Dr. Banner would do. If I make Dr. Banner angry, and I'll talk about this, why not talk about it right now? If you make Dr. Banner angry, I'm going to access that Banner object, access its state variable, and set his state variable to a new instance of the Hulk, and pass that Banner object back to the Hulk, so the Hulk knows which person he's attached to. So now this is what we call a state transition, where one state on certain method calls, certain API calls, is going to update the state of the object to which it's attached. When you calm Dr. Banner down, nothing really happens. I'm just printing to the screen because, you know, just to show something. But nothing really happens. He's already calm. If he uses a car, he can drive it just fine. If he's in a fight, he's probably going to get severely injured. So that's not gonna go very well. The Hulk, on the other hand, you make him angry. He's already angry. If you calm him down, he's going to change. Bruce Banner is going to change his state back to Dr. Banner. If he uses a car, he's just going to smash it. And when he fights, he's going to smash again. Use car and fight, he's just going to smash. That's what the Hulk do. So now when I write each of one of these classes, my code is quite simplified because each method that I write, I'm only thinking about what is the behavior for this method in this state. I don't have, whereas if I wrote the make angry method here, I would have my conditional. If I'm in the Dr. Banner state, do one thing. If I'm in the Hulk state, do something else. Now I'm simplifying my thought process. Once I have this set up, each method is very simple to write. I'm only thinking about one method in one state, and that's it. I'm limiting my thinking, and importantly, I'm limiting my testing. If I want to test this method, how does the Hulk fight, I just call this method and make sure it does what I expect it to do in that state for this API call. I'm not trying to call it up here. I mean, I guess we do in our testing for these, but we can test at a lower level, a more granular level. So we have more methods to test, but each method is easier to test. Yeah, so each state that your object can be in, you create a new class for that state. Extend the state abstract class so you can store that state in a variable of type state. And I should have warned you, I'm going to say this word state so often in this lecture, it's going to lose its meaning. So just a heads up on that. But we were going to store that in a variable of type state. So we have to extend that state. And by extending it through inheritance, we're able to use polymorphism and store objects of type Dr. Banner in an object of type state and objects of type Hulk in an object of type state, or a variable of type state, through polymorphism. And that's what gives us the behavior we want. So this dot make angry, or this dot state dot make angry, this might be calling this method, it might be calling this method. Which method is actually called depends on the current state of Bruce Banner, which depends on the type of the variable that's currently stored in the state variable named state of type state. Could we get away with changing state to avail? No, because we do have to reassign it here and here. We are reassigning it. And by reference. So we're overwriting the reference. Sometimes we can get away with that if we're storing a reference and only the state variables of that reference are changing. But here we have to change the reference itself. Yep, so Bruce Banner, we're going to say he starts as Dr. Banner. And then if you call make angry, he's going to become the Hulk. And then all the functionality here swaps over to the Hulk methods. It's losing meaning already. State, state, state. All right. So let's take a look at this. I might have got ahead of my slides here. I explained a lot on that one slide. Yeah, I really overdid that slide. So we do have the keyword this. So Bruce Banner is going to have a reference to himself in this class in the keyword this. And when we create the initialize the state variable, we're going to initialize him to a specific state, Dr. Banner here, and we're going to pass a reference of himself. So Bruce Banner is going to pass a reference of himself to the Dr. Banner object that's being created, and that's going to forward it to the state and assign it to this Banner variable of type Bruce Banner. So each state has a reference to the object to which it's attached. It's very important. So then the state itself has access to the state variables. In this case, we only have a state variable for the state itself. But if we had other state variables here, like for your calculator, you want state variables to store the left-hand side and right-hand side in the current operation that's going to be executed. You have extra variables there, and each individual state wants access to those variables. They also need access to the state variable itself so it can change its state. Dr. Banner can transition into the Hulk, so he needs to be able to have this reference to Bruce Banner so it can say banner.state equals new the Hulk of Banner. And then we have the state transitions. I usually wait till this slide, but I wanted to talk about it earlier. We have a reference to Bruce Banner. We have a reference to Bruce Banner in each state. This is a big reason why we have those references. We have a reference to it. We can access its state and update its state to a new state. I feel like I'm saying state even way more than I want to. So we can update that by saying new the Hulk of Banner. Make sure the Hulk gets that reference to Banner as well and can forward it to the state. And then and that replaces that state. So that after this line, This is how Bruce Banner is transitioning from Dr. Banner to the Hulk, is this line right here. Update that variable, create a new instance of the Hulk state, give it that reference to the object to which it's attached, and then assign it to that variable. Take a shot every time he says state. You won't make it. You won't make it through this lecture. I don't want to see you in the hospital. All right, so cool. That's the state pattern. You know what the state pattern is now. But why did we do all that? This seems like a lot of extra coding, a lot more complexity. We have inheritance and polymorphism and overrides and extends and constructors. It seems like this would be easier just to put all the code in the Bruce Banner class, and you'd probably win that argument. I'd probably concede and say, yeah, it'd be simpler. Just have your if statements and avoid the state pattern completely. Where the state pattern really shines is when we need to expand our code, add new features, and add new functionality, and specifically adding new states. So let's meet someone else. Let's meet Professor Hulk. So this is a third state that Bruce Banner can be in. He has all the strength of the Hulk, but he can drive a car, he's in control, and he's great in a fight. But we need a new state for this Professor Hulk. Without the state pattern, this is where we would be adding another else if and changing all our code and retesting everything that we've built. With the state pattern, easy peasy. We're going to create a Professor Hulk state. We're going to extend state. And we're going to implement those 4 methods. So what happens when you make Professor Hulk angry? Nothing. What happens when you calm him down? Nothing. What happens when he uses a car? He's going to drive it. What happens when he fights? He's going to smash, but he's going to be a little more careful about it and a little more precise about what he's smashing and have less collateral damage here. So, and that's it. We create the class, we extend state, and we do the same thing we did before, and just think about each one of these methods. And writing each method gets pretty easy. Calm down in the Professor Hulk state, what should the functionality be? Each time you write a method when you're using the state pattern, writing that method itself should be quite easy compared to the design of the program. You're spending more time designing and less time actually thinking about how do I write this code. Each piece of code you write, each piece of functionality is much smaller, much more modular, and much easier to write and test. And then we have to add our state transition. So it's not enough just to create the class, but we have to add some state transitions. For this, I'm going to do something a little different than we saw in the previous transitions, is I'm going to put the transition right in the Bruce Banner class itself. I could put this in the state API, this learn control method, put it in the state API and have my other, and define what Dr. Banner and the Hulk, what they'll do when the learn control method is called. In this case, I want Bruce Banner, whether he's Dr. Banner or the Hulk, if he learns control, I want to transition to the Professor Hulk state. So I'm going to put that right in the Bruce Banner class itself. So no matter what state he's in, if he learns control, he's going to transition to Professor Hulk, and he's going to have this functionality. And notably, once he's Professor Hulk, he can't go back to either of the 2 states. There's no state transitions here. There's no state transitions accessible here, except becoming the Professor Hulk again, which isn't really a transition. So once he's Professor Hulk for good. And notably, I didn't even show the other 3 classes because I didn't change a single line of code in the other 3 classes. Again, I could have added learn control to the state abstract class and then implement what happens in each one and then just write this state transition in each one of those. So I might have been changing a little existing code or at least existing classes, but even then, I wouldn't be actually modifying any existing behavior. I'm just adding another method that I have, and then I test that method. Oh, stuck is Professor Hulk. Yeah. Whew, I was scared there. Yeah. Heck yeah, S words. All right. Yeah, he's stuck as Professor Hulk once he transitions into that. So I think I said all this. I don't need to, especially with 1 minute, I don't need to stand on that slide anymore. So with the state pattern, one thing that's extremely helpful with this, because as you'll have more states and more classes and just a lot of code all over the place in your project, you could argue that the code is getting more scattered across different classes. To see how Bruce Banner behaves, you'd have to click through a lot of different files, 3-4 different files if you count the state abstract class, to figure out how he actually behaves throughout all this behavior, throughout all these API calls. So what helps is getting some documentation in the form of state diagrams, which shows all the states that the object can be in and all the transitions between those states, specifically which method calls are going to cause state transitions. So when we start in the Dr. Banner state, and if make angry is called, if calm down is called, or anything that's not listed, you stay in the Dr. Banner state. Make angry is called is going to transition to the Hulk state. Calm down is called is going to transition back to Dr. Banner. And in either state, learn control is going to transition into Professor Hulk, and then you can't get out of the Professor Hulk state. He's going to stay in that state. So this way of visualizing all the state transitions can help understand what the code is doing without having to click through all those files. And then you just click through, okay, the Dr. Banner state, what's the behavior here? Open up that class to see what the implementations are of those methods, those API methods for that state, the Hulk state, Professor Hulk state. Makes it easier to wrap your head around what's going on. And I will say this a lot. I will strongly recommend, before you type a single character of code for these 3 lecture questions this week or the homework assignment, anything using the state pattern, draw your state diagram first. That's probably something you're going to hear in office hours. I hope all my TAs ask you, show me your state diagram, because you need to understand what you're writing. If you're trying to just dive into the state pattern without planning ahead, it's not going to work. Where that might work with other approaches to coding. With the state pattern, draw your state diagram. Even when I drew up my solutions for the homework assignments and even these lecture questions, first thing I did, I got an old-fashioned pen, an ink pen, and a sheet of paper, and I drew out some state diagrams, and I drew them out until something made sense to me, and then I finalized my design, and then went to coding. You should be doing more pen and paper work or whiteboard work for these questions, for these state pattern questions and homework, than actual coding. Once it comes time to do the coding should be pretty easy. You might hit a snag or two that's a little tricky to figure out, especially with calculator. There's some kind of tricks there that need to be figured out. But when it comes to actually writing that code, it should be a lot easier than the design. The design is going to take a lot longer. It's very much a design homework, not a coding homework. So keep that in mind. If you dive right into the coding, you're probably going to spend way too much time on this homework. And my recommended approach for the design pattern is figure out your API. What methods are going to change behavior based on the current state of the object? For this lecture question, that's given to you. The API is given to you. For the homework assignment, it's kind of given to you as well. It's actually, I think I did put it in the handout now. It's all the buttons on the microwave or all the buttons on the calculator. That's your API. API is pretty easy there. And then one extra for each one just to get the current state of like what number is displayed on the calculator. And then decide which states exist. What different situations can I be in where the behavior should be different? Each one of those is going to be a new class extending your state. Your state abstract class will define your API. In each concrete state, create a class that extends that for each state that can exist. And then determine what transitions, how do I move from one state to another? Which brings us back to the lecture question. So Wednesday and Friday will be examples of using that, and I'll go through this for in the examples, and then show you the thought process of going from a problem statement like this to designing the state pattern, making a state diagram, and then finally implementing it and writing the code. Where Wednesday will be looking at the jumper, how jumper was designed. And then Friday will be a brand new question from scratch, which I have some examples. In the past, I've asked the class to come up with an idea, and then I would just turn it into a state pattern question and do everything on the fly. So I might do that again if I'm feeling bold on Friday. If not, I'll just take one of the ones that students came up with in previous 116s. That's more boring. I'd rather do a new one. It puts me on the spot. Forces me to really show you the state pattern and the design behind it. Can you explain the lecture question again? Oh, this lecture question? Yeah, absolutely I can. So you want to create a player class with these 5 methods, and technically you can cheese this one. I've seen students cheese this one before without using the state pattern, but I don't recommend it, because the whole point of this question is, and the next 2 lecture questions, is to ease you into the homework so you understand how to do the calculator or microwave homework assignments. These lecture questions are strongly designed to help you get into that. It's just a gradual progression of difficulty. If you cheese this once, you're not helping yourself. So, yeah, my dog out there barking at nothing probably. So I'll say this in terms of the state pattern, expecting you not to cheese it. So you have your API methods already. Duck, standstill, run, jump height, and movement speed are all methods that are going to change behavior depending on the current state of the player. Your states are also defined for you. This player can be running, ducking, or standing still. So you have 3 states, and you have to determine what the behavior of these 5 methods will be in that particular state. For jump height, movement speed, that's defined for you again. And then the question is duck, stand still, and run. What should happen with these? The functionality is defined. So if you're in the standstill state and duck is called, you should have a state transition to the ducking state. If run is called, you should have a state transition to the running state. If stand still is called, you don't do anything. If the player is running and duck is called, nothing. Stand still is called, transition to the standing state. Run is called, do nothing. Then stand still, duck is called, do nothing. Stand still is called, transition to the standing state. And run is called, do nothing. Did I say that? Did I say stand still? I meant run. I did for the last one. Run, you can't go from run to duck, so that does nothing. Run to run doesn't mean anything, does nothing. And run to stand still, the player stands still. I think I said stand still on that last one. Stand still is duck and run both state transition. So that's the design. So this one is it's your introduction to the state pattern. All the design is there for you, but you have to implement this. You have to create a player class, create an abstract state class, extend that with 3 other classes for the 3 states that the player can be in, and then implement all these 5 methods in each one of those states and pass the reference to the player to which the state is attached to properly across all these states. And then when you're testing this, you're not going to call any of your states. Notice how the state names are, the names of those types are not defined anywhere in here, but the player is. There's a player with a constructor that takes no parameters. The initial state is standing. That's all defined. So when you're testing, you can create a new player. You should expect that player to be standing, and then you can call these 5 API methods in any order that you want to be able to test that player. So the player, in your testing, you create a new player object. You would expect it to be in the standing state. So the first thing you can do when the player is created is call jump height and say assert jump height equals 3, assert movement speed equals 5. That's the first thing you can do right when you create a new player. Then you might want to trigger what you expect to be a state transition, maybe call the duck method, and then call jump height and movement speed again. Now we expect jump height, assert jump height equals 4, assert movement speed equals 1. Then call some other combination of these methods, whatever state you are expected to be in based on this functionality. Call the jump height and movement speed again and make sure that they're returning the right methods. So you can only test by calling these 5 methods. Just remember that we're testing things a little indirectly here. We're going to call these methods figure out, what, according to our state diagram, what state we expect to be in, and then assert the jump height and movement speed are correct according to that state. Does this look more interesting than the 116 I had with Hertz? Well, I mean, to be fair, this is one of my more exciting lectures. I'm happy with this one. Anytime I can get a reference in there. I have boring lectures. Lecture question for a simplified. So the lecture questions for this week are actually posted already. The graders are all released. The Friday lecture question, I believe that one's the car. I believe Wednesday is the TV and Friday is the car. Those might be reversed, but it's a car and shifting gears. In each gear, what should the pedals do? What is supposed to happen when duck to run is called? So when you're in the ducking state and the run method is called, nothing should happen. You can just have a blank method. Open brace, close brace. Stand, then run. So if it's duck, if you're in the ducking state and you call stand still and then run, you should then be in the running state, because stand still triggered a state transition to the stand still state, and then the call of run in the stand still state triggers a transition to the run state. Yeah, thanks, Dennis Grace. I like this lecture. So this lecture, I joke with the TAs about this still. This lecture used to be the worst lecture of the course, like kind of by a long shot. I had this tic-tac-toe example, which just didn't make sense at all. And I was so ashamed of it. I'm like, I'm going to spend a ton of time and just make sure this lecture is awesome. Because it's important to know what the state pattern is. It's a pretty complex thing. So I'm like, I need this lecture to be good. And it's one of my worst lectures, probably my worst lecture. I had this tic-tac-toe example, which was just confusing as all hell. Even when I was going over that lecture, I'm like, what was I thinking when I made this thing? Really confused the class. Nothing made sense. So I revamped the whole thing. So now it's one of my best lectures. I'm happy with it. You do have to make the abstract. So do it small. You do have to make an abstract class. So you will make an abstract class, and you'll extend that class with concrete states for run, duck, and stand still. But you won't test those directly. In your test suite, so like for example, you don't know what I'm going to call my states. I might call it player running, or the player is now ducking state. You don't know what I'm going to call those. So you can't test those because you don't know what mine are going to be called. And more generally, you want to test the API. You can write out there in the real world. You can test your specific functionality. Just create a standalone instance of the run state and then test its functionality. And you probably should do that. And you still can do that in this class. Just don't submit it to AutoLab because it'll crash. It'll break. But you do want to test the public interface. This is how other people are going to be using your code. If this is part of a larger program and people need this player class to be instantiated and then actually move around this platformer game, this is how people are going to use it. So this is what you really need to be correct. If the internal details are less important to people using your class. So this is what we need to have proper functionality. We need these 5 methods to always be correct. So that's what we're testing here. So that's kind of the idea of what we're testing. And then the other functionality, the actual abstract class and the state transitions and all that, how that happens. To the outside world, nobody even cares that we're using the state pattern. This could be a whole bunch of if statements in one single player class. Nobody cares. We care that we get the functionality that we want that's defined by the game. The game designer said when the player is ducking, they can't go from ducking to run, and here's the jump heights and movement speeds. That's the stuff that people care about. Does the game work? All the rest is internal details to our programming process. So that's kind of the idea of the testing here. Plus, it's a practicality thing that if I do say test all the other classes, then we have to give those names. And now it's more stuff that I'm going to make you test, and it's more names, which means more opportunity for typos. So there's practicality to it too. What does player not have to be? So player's not abstract, just like Bruce Banner was not abstract. So the object or the class that's going to contain the state is never abstract, because people in other parts of this program are going to have to instantiate this class and then use these API methods from that class. So that's never abstract. But the state class itself, this type here, that'll be abstract. It doesn't have to be abstract, actually. But I like making it abstract for lectures just to make sure we get the idea of what an abstract class is supposed to be. No, you don't do it with one. Yeah, do it small. Maybe I misread that before. But you're only testing one class. No, I did say that. You're only testing one class. There's only one required class that I give a specific name to that you have to have. But with any lecture question and any homework, you can always create more classes and more methods and anything else that you need to complete the question, the problem at hand. So you can create a state abstract class, a run class, a duck class, a standstill class, and then use those in your player class and in each other to have the state transitions. They're just not part of the definition of the question. That's not part of what I'm requiring. You will have to do that to complete the question, but it's not. I'm not going to say create a class called run, and I want you to be able to do that on your own, because that's what you have to do with calculator and microwave. How player has 5 movement speed if the player is standing. So if you're in the standing class, or if you're in the standing state, the movement speed method should return 5 as an int. So like when we implemented the fight method in the Hulk, we define that to be return or just print to the screen Hulk smash. It's similar here. In your standstill state, when you implement the movement speed method, it's a really simple implementation. You just hit the 5 key on your keyboard, boop, and that method's done. But setting up the state pattern is what we're practicing with this lecture question. (116) rewrites the laws of physics a couple of times too with physics engine. It'd be fun to make physics engine a bigger homework. I mean, it'd have to be like later in the course or something. But it'd be cool to build like a fully fledged physics engine with all kinds of interesting features. With the as far as I was willing to go so far for homework 1 was the expansion objective of having dynamic collisions. So two players can collide with each other. Have those kinds of collisions. Just makes it more interesting. The floor is slippery. I think I'm missing a joke in there. If you're standing... I see what you're saying. I'm saying if you're standing... I mean, yeah, I did call it standstill, didn't I? Oh, well. I should have had that called walking or walking upright or something. Yeah, I get you. I get it. Yeah, do it small. You got the idea. Yeah, you want to mimic the structure that we saw in lecture. Use that as your example. You're going to follow pretty much that same structure, just with a different application. I want to make sure it's my way of making sure you understood what we talked about in lecture, which I guess is every lecture question. You can't directly test your states, but you create a new player and then call these 5 methods. Call these 3 methods, and then whatever state you expect to be in, assert that jump height and movement speed return the values that you want. The coefficient of friction is always 0. except you can run fast too. So I don't know how this player can run without any friction, but they can definitely run faster. Can I use my comments in the homework verification, or should I delete them? The homework verification. Oh, that's a good question. I mean, as long as... Ooh, that is a good question. Because what's stopping somebody from just writing comments and then... I'll say, at least for now, I'll talk to the TAs after all the interviews and see how it goes. But I'll say for now, you can leave your comments in there, but when you're asked questions, you can't just read your comments. So, because you're expected to interview and on the fly be able to explain your code. If you have comments in your code and you're just reading your comments, no. But if you have some comments to help you remember what you did, and you're clearly expanding upon those comments, and you're saying much more in-depth stuff than just what the comments say, then sure. But if we start noticing students just reading their comments, or effectively reading their comments, then we'll have to put a stop to that. So someone can ruin it for everybody. We're at 442. So let me just skim through these and make sure. When do you think the singularity will hit? Like within 50 years, probably. That's a deep question for 3 minutes left when you typed it.